This then leads to, you have all these microstructures you could build now, right? So then this starts to lead you into, well, for different rock, what should I do, right? And the answer is, I don't know. So here's a granite with all these minerals that have grown together. Here's a basalt with these minerals in a matrix. Holy smokes, you know, so as a granite, maybe we could make flat jointed with spherical grains. Maybe we could use subspring network with Voronoi grains. This one for the matrix, it's all kind of viscous. Maybe you could use soft bonded things, right? You have a lot of choices essentially. So I like to sort of, if I think about this, there's sort of a progression of, these are compact rocks, granite. So granite has complex shaped grains. They're well interlocked. Marble has simpler shaped grains that are well interlocked. And sandstone has all kinds of initial void structures and these grain sutures, which, you know, are going to have various radiuses and lengths, right? These are different microstructures, right? Why do they happen? Granite, you have a melt and crystals, it cools slowly. So these crystals form and grow together. That's why you have these complex shaped grains with very well interlocked boundaries, because these crystals have grown outwards and interacted with each other to form that system. Marble is a totally different situation. You have a limestone, which is a bunch of little sea animals that fall to the bottom and get squished together to turn into a limestone. And then you metamorphose that thing. And in that metamorphose process, it ends up creating these crystals. And these crystals grow in such a way, it's interesting that they form these much more polygonal structures, right? And then, as you know, sandstone is a bunch of rock fragments that get cemented together, right? So they can have a whole range of sizes, but typically they're sub-rounded, right? So here's ideas, right? If I had to do this now, a granite, well, I'd use probably that subspring network Voronoi system that I just really quickly flashed at you. Marble, maybe flat jointed spherical grains would be sufficient for that. This thing, this is potentially better. Maybe parallel bonded system is sufficient because we can control the radius, for example, of the cement in here, stuff like that. Maybe that's sufficient. All right. Let's talk now about joints. Okay. We want the joint to behave as an interface between two surfaces, right? So what we can do is, if we want to put an interface into an existing bonded assembly, we can use a collection of a special contact model called a smooth joint contact. What does that do? Look at this first. There's an initial packing of yellow discs, and those are initially connected with parallel bonds. That's the double black lines. Then what we do is we say, insert a smooth joints, two of them. The joint conceptually is this blue line and this other blue line. What we do is we say, let's find all the contacts that have particles on opposite sides of the joint. Those are the red guys. So you can see they're not perfectly aligned. They're kind of up and down and up and down, okay? Each one of those is going to get this smooth joint contact. And what it's going to do, here's a typical case. Here's that blue interface. Here's a particle on one side. Here's a particle on the other. Now, if you just have a normal contact model here, if I shear the top upwards, there's a normal force that builds up, and these particles have to ride over each other. And so you get this interlocking that's occurring. And that interlocking is occurring and giving you a shear strength, for example, but that's going to be totally a function of the size of the particles, because this is like asperities riding up against each other, right? These are like unbreakable asperities riding up against each other. So if you just found these contacts on opposite sides and just put, say, the linear contact model with zero friction, you're still going to get a big frictional response. You're going to measure a macroscopic friction because these guys have to ride up over each other, okay? Instead, we make this special smooth joint contact that effectively works out the mechanics to pretend that this contact looked like this. It's going to behave as though those two particles were carved off like that. And so now we're able to provide contact properties essentially in this joint system. So we're going to have a normal stiffness and a shear stiffness, and we're going to have a cohesion and a friction angle. And so now when we set the friction angle or the friction coefficient of this system, we can then do a sliding thing on this, and we will measure that macroscopic friction coefficient. So here's the example in 3D. We wanted to make a joint, which was a big plane. You find the contacts between balls on opposite sides. We're looking straight down the edge of it. You can see there's kind of this cloud of them above and below. Okay, there's the contacts, there's the joint. We take that system now, we're looking at it in 2D. We take this system of bonded material, we fully fix the bottom, we turn on gravity, okay? And here's the 3D version of the same thing. We fix the bottom, we turn on gravity. We assign a joint friction coefficient of 1. Nothing happens. It holds up. Then we're going to change the joint friction coefficient to 0 and run it, and it's going to slide. Okay? So this is a way of putting joints into a bonded assembly in such a way that you can specify joint properties and you do not get this bumpiness effect. And that's why we call it a smooth joint, because that's a joint is an interface between two things, and that interface is behaving as though it was smooth. Okay. But remember, it has properties. It can have a friction coefficient. Okay. But it's the bumpiness that's getting removed. Okay. So let's just look again at some of the work people have done using these different types of microstructural models. So here's where we take a bonded system and we just carve out particles to begin with. This is actually deep underground at Yucca Mountain. Yucca Mountain was where the US was originally planning to store its low-level civilian radioactive waste. And so they have a big drift down there as part of a research facility. And in that drift, the rock itself is called lithophysal tuff. The rock has all these voids in it. And the voids range in size from millimeters up to meter. There are voids in here that are the size of meter. Most of them are the size of like baseballs. Okay. So for that work, they needed to do all kinds of modeling. They needed to do continuum models because they needed to do big, large regions of the tunnel. But they needed to get some idea of how all these voids in the system affect the, for example, the UCS and the modulus. And most of the cores they took, they were not able to take big enough cores to like test the effect of these voids. So they resorted to doing these PFC 2D models. So we bonded a material. This is a geologic mapping. You can see it's a 1 meter scale of the wall. A geologist went through there and outlined all these different voids that were cut. He then overlaid that outline on top of this. You can see this guy, all the particles with centroids inside got removed. Then we take this thing and we basically do a giant UCS test on this 1 meter square chunk, which corresponds to the 1 meter chunk here. And here's the axial stress strain curve, right? And here's the damage. And so, oh, we got a UCS. And then this was done for there had like, I think 40 different locations along the drift. And so we made 40 of these, and then we were able to get like, what's all the different UCS values and what are the, you know, what's the distribution of the UCS values? What's the distribution of the modulus, stuff like that. Okay, so that's an example where you're removing grains. This is an example where these are cross sections of a concrete. You can see the aggregate and the darker stuff is the cement paste. And this is just showing some of that work that was done where I mentioned it, where we overlay this onto the bonded system, identify different groups, give different properties to the yellow, different properties to the white, different properties to the interface. And then this was a whole PhD thesis where Tatiana looked at this stuff and then made comparisons between the breakages and like some of the fractures that they saw in their experiment. Okay. This now is the smooth joint idea on steroids. Okay. If we want to represent a rock mass, what we can do is do something like this. This is actually the scale of this, I believe, is almost 1 kilometer by 2 kilometers. And this is a big mapping of a joint set. There's 8 joint sets overlaid on each other to describe, that's a real set of joint sets that were mapped geologically. And what they then did is every single one of those joints got inserted as a smooth joint that we just talked about before. And so you just keep carving the thing up. And so you get these blocks. These red guys are still all connected, but you get partial joints in the middle. You get intact material. You get a crazy complicated thing. This crazy complicated thing we refer to as a synthetic rock mass. Okay. And so these things have been used by people to actually try to look at the effect of the jointing structure on macroscopic behavior. What's the overall effect on strength of the jointing structure? What's the effect on modulus of the jointing structure? Things like that. So these are, again, the type of structure, microstructural models that one can create, synthetic rock mass models. There's just a zoom in of that thing. This is actually a poster that I have in my office. This was actually created for a guy who was retiring from De Beers, the diamond company. De Beers was one of the original funders of the PFC development back in 1995. And when this guy retired, we made him a big synthetic rock mass model and like made this poster for him. So there's the idea. Now we can do a lot of cool things now that we have these joints. Okay, so here's another. I'm going to call this a grain-based model. Okay. What do? We take a grain structure. In this case, we just generated this and we use the Voronoi tessellation in 2D space. So you can see the outline. These things perfectly fill space. So this is a given grain structure. We start with a bonded assembly and we overlay this onto the assembly. And if you keep zooming in, it looks like, oh yeah, each one of these edges is going to be inserted as a joint into the bonded system, right? Just like we talked about before. What do we have now? These interfaces are deformable, breakable joints. Internal there, it's a breakable, deformable, breakable parallel bonded material. So now we can have grain breakage. The grains will break naturally. So there's breakage of the grains and you can control the interface behavior. And the interface behavior can have partial damage. And after after the guy partially damages, he's frictional. Okay. So this is what we define as a grain-based model. And here's an example, a more recent work of people using PFC. This is 2019, where they built this grain-based model. Here they looked at the different mineral types in the rock: quartz, plagioclase, feldspar, biotite. Those are the colors, right? They somehow generated these shapes. I can't remember how, based on some discretization of this into mineral separate grains like this. Then they colored them based on the type. And then just like before, they put in these smooth joint contacts at all the boundaries here. And then inside of this grain, there was different properties. If it was quartz, then plagioclase, right? The inside of these grains in this case wasn't parallel bonded. It was actually flat jointed material. Okay. And so that's an example. They take that thing, they do a UCS test loading it vertically. And here now they're looking at all this different interesting damage. Some of it's going through the grain, some of it's going at interfaces, etc. Right? So here now they're able to map in the microstructure of a grain system into this type of model. These grain-based models have been used by many, many people now to look at all kinds of interesting phenomena. They're almost all of the ones I've seen are in 2D. So that's the caveat with this stuff. It gets much more complicated to do it in 3D, but there's no conceptual reason you could do it, because you could start with a Voronoi tessellation in 3D, and those faces give you the joints that you would add with smooth joints. But I haven't seen anyone actually do that. Let's look at a few different examples now. Okay, we got like 10 minutes. Let's see if we can get through this here. We're going to look at, well, we're going to look at ceramic beads. What the hell, ceramic beads? Why are we looking at that? We're going to look at undercutting of backfill, and we're going to look at flour milling. I bet you didn't know we were going to learn about flour milling a little bit here. Okay, then we're going to talk about more rock stuff. Ceramic beads. look at this. If we take a collection of spheres and pack them into the shape of a sphere, we get this bonded system that's spheres. And we give them parallel bonds, and then we just do a compression test on that sphere, a diametral compression test on the sphere. And what do we see? We measure force deformation. Oh, look at this. This matches the Hertzian response for an elastic body being squeezed. Okay. That's good to know. And then it breaks. And so and here's how it's breaking. And it forms these failure planes. If you look down on it, they look like they go across and then they go across each other. And again, this is very much like what we see when we really break solid beads. This also then allowed us to make hollow beads, where we then just carved out material on the middle, but we still had a shell. And we looked at that sort of behavior. There were people from somewhere. Does it say on here? JPL, Jet Propulsion Laboratory, some kind of a group there that was looking at the behavior of giant packings of these glass beads, some of which were hollow and some of them were solid. This is an example of work that was done with PFC 2D to measure backfill. So this is a big, huge stope. You can see this is 35 meters across and probably 100 meters high. This material is mined out, and then they put in cemented backfill, and then it becomes hard and solid, and then they come back later and they start to mine underneath it. And here they're just going and making an undercut. All of these undercuts are 15 meters. And you can see that the backfill, as you increase the UCS of the backfill, you get less and less breakage. Eventually, if you make it strong enough, it doesn't break at all. All right. Then if you look at this case, this is with the UCS of 1. So first we'll look at the UCS of 0.5 and we undercut it, and you can see it's not quite strong enough. So this is the bonded system, right? This is cemented backfill that's been micro properties chosen to have a UCS of 0.5, and you can see it's failing. The whole thing's going to eventually fail. If I get out of there, and now instead of I make the UCS 1 MPa, now you're going to see that it's going to fail, but it's going to stabilize, and you're just going to see this broken material here. And now we stabilize. And the thing I showed you before, of course, was looking at these final shapes with different values of UCS, right? So this is a useful thing. They were looking at cemented backfill. Okay. Okay, listen to this. Flour milling. The whole idea here. Can we build a microstructural model to mimic the physical microstructure of a grain of wheat? That's the challenge. Okay. And if we can, and if we can confirm that that model is quantitatively behaving correctly, then we could use it to study flour milling. Okay, we did this for a client. I can't tell you who. Okay. So the first thing we have to know is what is the microstructure of a grain of wheat. This thing is about 5 millimeters, right? I don't know if I'm a city guy, so I never really looked closely at a grain of wheat before, but think of a kernel of popcorn or a kernel of rice. It's about the same size, right? And so this kernel of wheat has this relatively hard outer layer, which they call the bran. And there's a super small amount of material here called the germ. This is where the seed is that starts. The seed is shielded by the bran. The seed needs energy to start to grow. It comes from the endosperm. That's 83% of it. This endosperm is naturally white. When you do create flour, what you do is you run this through mills and you crack this thing open. You sift away the bran, you sift away the germ, you're left with the endosperm, and you just keep on grinding it smaller and smaller. Okay. The way that it gets ground is you have these two big rollers, these metal rollers. They're both rolling downwards, you can see. This one rolls faster than this one. The result is the kernel gets pinched between these teeth, and now it's like a Brazilian test, and it naturally splits into two. That's how flour milling works, okay? If you zoom in to endosperm, okay, here is the 400, this is, you can see 400 microns. All right, this is very small. If we zoom in even closer, what do you see? Flour itself is made up of broken pieces of endosperm. That's why it's white. And these broken pieces, as you can see, 100 microns, they're quite small. That's why if you put flour in your hand and you look at it with your naked eye, you cannot resolve the grains. But it really is made up of this whole crazy size distribution of grains. Okay. Now, what the heck is inside of a grain? You can kind of at this scale sort of see these weird particle-like things. These are granules of starch. Okay. And what you have is granules of starch that are embedded in a matrix of protein. Okay. Here's a cross section through there, 30 microns. There's the starch. They've been cut. There's bigger size starch that are shaped like lentils, like the stuff you eat, lentils, squished out spheres. And there's smaller starches that are nearly spherical. And you can't see it in here, but these are embedded in a matrix of protein. Okay. This is what endosperm is. Two things, starch in a matrix of protein. Now, in order for us to gain any insight, understand if our model makes sense, we needed to compare to something. So lo and behold, in 1990, there was a guy in this industry who said we need to start to measure properties of our grains, and we need to do it by doing conventional material science tests. So he took a kernel of wheat and he used a little tiny grinder and he grinded off the bran. So he's left with this little hunk of about 4 millimeter size of endosperm. Then he took a lathe, and it's called a watchmaker's lathe. So it's able to turn very, very small cylinders. And he carved off with the lathe this. He made a cylinder, okay? And then he carved another one into this shape. For this shape, he took a bit of super glue and he glued it onto two platens and he pulled it and he measured the stress strain curve for a tensile test. For this one, he glued it onto two platens and he squeezed it and he measured the stress strain curve for a UCS test. The question is, what do those curves look like? Okay, look at this. Look at this. This is so cool. First of all, here's the stress strain curve. It hardens a little bit, then it goes up and it breaks, and then it breaks, then it breaks. Notice the stresses, 40 MPa. Okay, this is kind of like a rock. This is essentially a relatively brittle material. Notice there's three different classifications here. We talk about soft wheat, we talk about hard wheat, and we talk about durum wheat. Durum is actually a Latin term that means very hard. That's what the word durum means. We use these. Why are they different? Because microstructurally, as you go upward of these different types of wheat, you have more protein in there. It's tighter packed. So as you tighter pack it with protein, notice the stiffness gets bigger, the slope, and the strength gets bigger. Okay. This protein, by the way, is called what we call gluten. You've probably heard of that nowadays. People talk about gluten-free flours and stuff. That's where they somehow take out the protein. And then these different wheats are used for different products. The soft wheat is for like cakes and biscuits. The hard wheat is used for bread, and the durum is used for pasta because they have all sorts of different properties when you mix them with water. And there's a whole different set of microstructural physics that go on when you do that. We're just concerned with the dry grinding of these. All right. So we had this data. So it's like, oh my God, we could do this. This is just like rock mechanics. We can do tension tests and compression tests. So what kind of model did we build? Here we go. And I know we're going to end with this. We just did the same thing we did, but that you saw before. Notice we have three shapes of particles. We have these big guys, which are starch A, and then we have these smaller guys, which are starch B. The smaller guys are spheres. These guys are lentils. They each had a size distribution. Then they're flooded with these yellow guys, which are supposed to be the protein. Okay. And so, okay, look, and these are rigid blocks. These two guys here, they're rigid blocks. You can see the discretization of triangles on there. And so we basically create these bigger particles that are the starch. We flood the system with protein. We squeeze it. We get it packed. And now we give different properties to the yellow guys and different properties to these. You know, you get the idea, right? We give different properties to different parts. So this is what that looks like. There's the result. This is what it looks like if you look at each of the individual components. So this protein matrix is filling all the space. That's why we use small little yellow guys. Then we performed the test. You guys know all about this, the UCS test, the tension test. And this is what this looked like. One of the thing we varied, if you remember here, was you should start to get stronger and stiffer if you have a tighter packing of protein. So for our model, we put in X amount of volume fraction of protein, then we put more protein, then we put more. We just keep putting in more yellow particles. We measure that based on volume fraction of protein. So, and then we do the UCS tests. And we ran 10 tests because we had 10 different instances. Remember, you set the random seed, you get 10 different instances. You get natural variability in these type of models for the properties you measure. So there you go. There's the UCS. Here, these stresses were quite low. They were 5 pascals. This was an initial model to see what was going on. And notice as we have lower volume fraction, less protein in there, it's weaker. They have the same y-axis, right? So that's interesting. We do the same thing for tensile strengths. There's again a variation of tensile strengths. The less protein, the lower the strengths. And that's all I'm going to say. We were able to show that we could match the hard and the soft wheat by simply changing the volume fraction of protein, which is our understanding of the actual physical mechanism of why those curves look different. So then the idea is that we verified the model, it makes sense. And so you could actually use it to stimulate milling. And so you could, this is an example, this is a 3D actually, and it's a cross section through a 3D chunk of this microstructure. And we started to load it like a Brazilian test like this. And we're looking now, we're coloring these based on fragment. So all of the blue guys mean that I can traverse to all the grains, I can reach them with intact bonds. Okay, so this is a fragment. And you can see then how this thing is fragmenting and breaking up into different size pieces. Okay. The last thing I'll say, and this will wrap it up, the reason they were interested in this was they wanted to develop a milling process such that when they run it through the mill, it will break apart into starch particles that are not broken and protein particles. They wanted to keep those separate and separate them out. And so they're in the process of developing a special chemical pre-treatment that will go inside the endosperm before the milling. And what it will do is preferentially attack the interface of the starch protein. And so basically they can selectively weaken that interface. The idea is if you weaken the interface enough, hopefully the starches will break free from the proteins. They have a lot of chemists who could do all the fancy chemistry, but they have no people who do computer modeling of fracturing. So that's how we got involved. So this was a model we developed, but this is I show this because I think it's a good example of the type of stuff that you can do with this type of bonded particle system. Okay, and it turns out it's brittle. It's very much like rock. So we've reached our time. We're going to finish this tomorrow. Okay, and there's more examples. We're going to show these examples. This time we're going to be about rock. And then we're going to give a little lecture and introduce this material modeling support package, and we're going to work with it. And we're going to build a sandstone, and then we're going to play with the micro properties and see how we can degrade it. So we'll actually be building material and testing it. Okay, because now that'll be pretty straightforward for you guys because you have an idea of this stuff. We're not going to be writing fish functions to do this. All those fish functions already exist. We're going to be basically just using them, setting parameters, running models, looking at how we visualize them, all that kind of stuff.